Hello everybody, so I'm recording this lecture because we have only 5 students online out of the 11 who should be here. Maybe there was miscommunication, I don't know. So please, for those who were not here, follow the course offline and so that we can continue without interruptions. Okay? So today we are going to talk about power. Okay? I'm sure you heard that word before. What is power for you? When you say that a car has a lot of power, what does it mean?
It's going fast.
It's going fast, and so in other words, it can produce a lot of energy in a little time. And a car which is not powerful cannot produce so much energy in the same time. Okay? And the power, you have the definition here. The power is energy divided by the time it takes to produce that energy. Okay? This is this formula here. W is a form of energy. W is for work. But here, in place of the W, we can put any type of energy. And if we divide the energy by the time, we get something in joules per second. Okay? And joules per second is a unit that we gave a name, and this name is the watt. Okay? It's the name of British physicist James Watt, who worked a lot on electric systems and electric motors, etc. Okay? Just there is one thing I would like you to be careful about. In this chapter, from now on, we will have 2 W's. We will have the W's, which is force times the distance. This is work. Okay? And we have another W, which is the unit of power. Okay? These two things have nothing to do with each other. There's different things. So be careful when you write not to confuse the 2 W's. Okay? One is work and the other one is the unit of power. Okay? So now, what is the watt? I told you the watt is joule per second. So a system which produces 1 joule of energy every second has a power of 1 watt. So a system which produces 2000 watt, produces 2000 watt, it's going to produce 2000 joules of energy per second. Okay? One unit you may know is the horsepower. You know where that comes from? The horsepower as a unit of power? Any ideas?
A horse.
Yeah.
Yeah.
Why does this have to do with horses? Yeah, well, because anciently, before we invented steam machines and motors and stuff like that, power was produced by horses. Okay, you know, in all the plants, in all industries, at some point in the industry, there was an axis with bars like that, and then on each bar, I'm going to have to draw horses. It's complicated to draw horses. Okay, and you had horses attached here. Okay, God.
Jesus.
Yeah, horses are complicated to draw. And
These ain't no horses.
but okay, we are not at Art Appliqué, we are in the college, so it's fine. Okay, so in old factories, for instance, doing fabrics, they needed power to power their machines, and so they had horses, and the horses would turn around all day long, and they would make this turn, and then this power was transmitted to the other parts of the factory via a system of belts. Okay, And so it's quite natural that the unit of power is based on the horse. Now let's imagine what is the power of a horse. Okay, the definition you have in the course is 1 horsepower is equal to 746 watts. This is now the official definition, okay, the official transformation of units. But how could we compute the power of a horse and do an estimation, see if we get to something close to that? What do you imagine? What could we do to measure the power of a horse? Aha. Any ideas? I don't hear you well. I don't hear you well. Speak more.
I said I don't know.
Yeah, you don't know. Okay. Well, take this example. This is one way you can measure the power of a horse. Okay, you take a horse, you attach a rope to it, you put a pulley here, and you ask this horse, you make it lift a mass. Let's take a mass of 500 kilograms, and you can tell the horse to lift this mass by 1 meter. Okay, and then you can measure the time it takes for a horse to lift a mass by 1 meter, and you can measure the power. What is the energy which is necessary to lift a mass of 500 kilos by 1 meter? How can we compute the energy? What do you think? You don't think? Come on, interact a bit. The energy, you can compute it as the work which is necessary to lift this mass, okay? And so the work is going to be the force that you exert on the mass, but this force is going to be what? If I have the gravitational force here, to raise the mass at constant velocity, I will need here a force which is minus the gravitational force. Okay? Do we agree with that? Okay?
Yes.
So this force, this energy, the work is going to be the force times the distance. Now the force is going up, its intensity is equal to the gravitational force, and the energy which is necessary, the work which is necessary to lift this mass is this. By the way, you will see in a moment that this is the expression for the potential energy. Okay? So the energy is now 500 kilograms times g, which will approximate to 10, and we said 1 meter. Okay? This is now 5,000 joules. Okay? This is one thing. Now, if we want to compute the power, we need to know what time it takes a horse to lift a mass of 500 kilos. So this we will guess it. How long do you think a horse takes to lift a mass of 500 kilos? Any idea? Just guess it. It's not going to be 1 second, it's not going to be 1 hour. Okay? But typically, if we could say 7 seconds, which is a reasonable time, this gives us what? This gives us a power of 50,000 joules. Sorry, I made a mistake. 500 times 10 is 5,000, not 50,000. Okay? So here this is 5,000 divided by 7. 5,000 divided by 7 is 714. 714 watts. the approximation is not so bad, because you see the definition is 746. Okay, so maybe the horse takes a bit less than 7 seconds. I mean, this is just to give you an idea as to where this unit comes from. Okay, are you there? Can you give me a bit of feedback, because I have the impression of talking in some kind of emptiness, and it's not easy. Okay, plus I no longer have the screen of Meet, so I don't even see if you are still online. Okay.
Yes, we're there.
Okay. Okay, so
Okay, let's go.
okay, the horsepower, we said it's a unit which is still being used. And why is it still being used? Okay, because the normal unit is the kilowatt. Okay, 1 horsepower is 746 watt, and this you can write as 0.746 kilowatts. Okay, so if you have a car and the car has a power of 200 horsepower, how many kilowatts is that? Can you compute that?
Perhaps.
Try it. Well, 200 horsepower, you do 200 times the value of 1 horsepower in kilowatts, which is 0.746. Okay, and so 200 times 0.746, exactly, it's 149.2 horsepower. Can you now tell me why the horsepower is still used as a unit? Sorry, kilowatt. Okay.
It's very nice.
Yeah, but what is the problem here? The problem here is that this number is lower than this number. And car enthusiasts, they like big numbers when they talk about power, okay? So if they change unit and they use kilowatts, it will give a smaller number, and they don't like it. This is why people like to continue talking in horsepower, although it's not a unit of the international system. Okay? But when you see ads for cars, you always have the power in HP and the power in kilowatts, which is the official unit. Okay? Okay. Now we have another unit of energy which I want to explain to you, which is the kilowatt hour. The kilowatt hour, how can you understand that? We saw that the power is the energy divided by the time. This means that energy is equal to power times time. Okay? The power is in joules per second, time is in seconds, so the result is in joules. It's an energy. Okay? And so 1 kilowatt hour, it corresponds to this multiplication. It's a certain power of 1 kilowatt times a time of 1 hour. Okay? 1 kilowatt is 1000 watts. And 1 hour, how should we write 1 hour if we want to compute joules?
In seconds?
In seconds, okay? So it's times 3600 seconds. Watts per second is going to give joules. And so if you do 3600 times 1000, you get 3,600,000 joules, okay? So 1 kilowatt hour is equal to 3,600,000 joules. Okay? And this is what you get on your electricity bills. Well, not you, your parents. Okay? 1 kilowatts costs something like 20 cents. So when you use energy with an electrical device, you can compute how many kilowatts it will give you, and you can compute the price. Okay? Let's do an example. Let's do an example. You have an electric radiator. Do you know the power approximately of an electric radiator? You have an idea?
No.
Electric radiators usually have a power of 2000 watts. Okay, this is very standard for an average radiator. Small ones maybe will have less power, but it's about the power of a radiator. An electric radiator of this power working 12 hours at night, how much is it going to cost you? Okay? At 20 cents per kilowatt hour. Try to do this calculation and tell me.
My calculator is
Sorry?
bugging. Wait,
Hmm?
mon calculateur est en train de bugger. Calculette.
Il faut la frapper.
Mais c'est mon téléphone. Je sais pas le faire.
So,
Tout le monde qui attend sur quelqu'un en fait.
sorry?
Non, rien.
Are you doing it or not? Okay, what is the energy that this radiator is producing? Okay, the energy is the power times the time. Okay, the power we said is 2000 watts and the time is 12 hours. So I have to do times 12 and then each hour is 3600 seconds. Okay, so let's compute that. 2000 times 12 times 3600. This is, oh god, this is 86,400,000. I don't know what's going on.
We can't see.
Yeah, I know it's my cam that disconnected, but it was working fine until now. And now, oh god, my phone has no more battery. Oh god, you know, when I'm using the camera, it kills the battery, and now I have to charge it again. Okay, so you have the sound, but you don't have the, but let's continue the calculation orally until the phone restarts. Okay, so it's 86,400,000 joules, and now how do you know how many kilowatts that is? Well, you divide by the number of joules in a kilowatt. So you do 86,400,000 divided by 3,600,000. Okay? You divide by 3,6, and this gives you 24 kilowatt hour. I'm sorry about the phone. I don't know how much time it will take to restart, but you can do it another way, this calculation. You can do it another way. You can say, okay, the power is 2 kilowatts, okay, and it's working for 12 hours. So 2 times 12, it's 24, and it gives you 24 kilowatt hours in the same way, right? And now if you have 24 kilowatt hours at 20 cents per hour, the price is going to be 480 Swissies. Okay?
Easy.
So you see, it's not that, it's cheap, but it's not that cheap. If you use an electric radiator for a certain number of hours, it costs you 5 francs every night, and so it's going to cost you 150 francs per month. Just like that. Well, listen, this phone, it's going to take a lot of time to start. What else can I do? I cannot do much else. We have to wait. Okay. Yeah, while you wait, you can now try to do exercise 2 on page 20. Okay? It's 2 cars. One car has a power of 250 HP. The other one has a power of 180 HP, and they both want to drive up a mountain pass, which culminates at 2,000 meters, and the valley is at 550. So you need to compute the time each car takes to go up the path at maximal power, not considering friction and all that. Okay? Can you try to do it? Number 2 on page 20?
Okay.
Okay.
Maybe, yeah.
And I hope my phone is going to restart soon. Oh yeah, it's restarting now. Okay, do the exercise.
You have corona and you're smoking?
How do you see I'm smoking? You shouldn't see.
Ah là là. Ah là là. Enfin, encore.
Yeah, you got me. Okay. Okay. And now we're back. Okay. Okay, I'll let you do the exercise. If you want what I wrote before, you can copy it here. Okay, so you have here the computation by using watts and seconds. It gives you 24 kilowatt hours, but you can also compute it as 2 kilowatts times 12 hours, and it's going to give you the same result in kilowatt hours. Okay, and then the price is 24 times 0.2, which gives you 480.
That's what I did.
Yeah. Well, the kilowatt hour is more practical for dealing with electric consumption in homes, but it's not the physical unit.
Okay.
Is everything working well?
Yes. All good.
You did it? So which car is faster, in your opinion, to go up the path?
The second one.
It's faster? The one
The
was
first one's
less
slow.
power?
No, the second one's slower. The first one's faster.
Ah, okay, the second one takes more time. What did I ask?
Yeah.
I asked the one which...
I have no idea.
Okay. Okay, so how can we compute that? First you need to compute the energy that you need. One thing I didn't tell you is the mass of the cars. Sorry, this is missing. So the two cars have a mass of 2000 kilos, okay? Because if they moreover have different masses, it's complicated, right? So, can I do the correction or you want some more time?
No, you can do the correction, I think.
Okay. So let's imagine we have a road which is going up the mountain. Okay, and this road arrives at a path which is at 2000 meters, and down here the altitude is 550. Okay, what's the total energy you need to lift a car up there? How can you compute that? Nobody? Well, the energy needed is equal to the work that you need to do to raise the car from A to B. This is point A, this is point B, right? Now this work, how can you compute it? If you go along the road and try to determine the angle between the direction and the gravitational force, it's going to be very difficult. We don't have the info to do that. But we can do a thing which is very interesting, and actually we will see that this is the general method. We can say, okay, the energy that I will need to go up here is the same as if I go flat, if I stay at the same altitude, and then I go up straight. We will see that in this kind of situation we can do this kind of things. What happens in this horizontal section of the road? In this horizontal section, the displacement is horizontal, the gravitational force is downwards, and the force we need to exert on the system to make it go up is a force here which is minus the gravitational force. Okay? D'accord?
Oui.
Good. Now on the vertical section, the gravitational force is pointing down, the displacement vector is pointing up, okay, and the force we need to exert is pointing up. What is the big difference you see between these two situations? Wake up.
Direction.
Yeah,
Direction.
the angle between the force and the displacement, right? Here we have an angle of 90 degrees, right? So what is the work going to be on this horizontal section? It's going to be how much the work for going here? I'm waiting. The angle is 90 degrees, so the work, which is the scalar product of the force and the distance, is 0 on a horizontal section, because the force you exert does not do any work. It's perpendicular to the displacement, so there is no work to go horizontally, but then there will be work for going up. Okay, for going up, the work will be what? I'm going to call it like this: work for going up, and this is work for going horizontally. The work for going up, you will compute it as the force scalar product with the distance. And now what is this force? What expression would you write for this force? Hello?
It's la gravité.
Yeah, it's this force that we exert it compensates the gravitational force. Okay, if we exactly compensate the gravitational force, this means we can go up at constant velocity because the sum of the forces is 0. And so here we have the force times the distance times, what's the angle here between the force and the distance? 0. Okay?
Yep.
It's the force times the distance, and we said that this force has the same magnitude as the gravitational force. So it's mg times the total distance, and the total distance, we will call it h, the height. Okay? So now I can compute that. The mass of the car is 2000. G, I will approximate it to 10. And the height is going to be what? It's going to be 2000 minus 550. Okay? So it's going to be 1450. And if you compute that, if you compute that, 2000, well, 20,000 times 1450, this is equal to 29 million joules. Okay, this is the energy you need to bring a car of mass 2000 kilos up from 550 meters to 2000 meters without friction, right? And now, how can we compute the time it takes? Oh my God, please say something.
We can use the formula from the exercise before.
Sorry?
We can use the formula we used just before.
Yeah, so we know that the power is the energy divided by the time. Okay, so what equation is that giving us for the time? You can write that P times T is equal to E. P times T is equal to E. So the time is going to be the energy divided by the power. Okay, the energy is in joules, the power is in watts, which are just the same as joules per second. If you do joules divided by joules per second, you will end up with seconds, and so it's going to be a time. It's correct, right? So now let's compute the time for the first car. The time for the first car is what? It's 29 millions, which is the total energy which is needed to go up the path. And the first car has a power of how much? Be careful now. What is the power of the first car? Hello. The power.
To convert it in kilowatts, no?
Yes, exactly. 250 HP. It's 250 times 0.746. Okay, so 250 horsepower times 0.746 kilowatt. It's giving us 0.746. It's giving us 186.5 kilowatts. Okay, so now I'm going to write that in watts, not in kilowatts. So this is 186,500 watts. So now I can divide here by 186,500 watts. Oh, sorry.
Thank you.
Yeah, tell me, because sometimes I forget. Okay, 200 HP is 186 kilowatts. It's 186,500 watts. So now I have to divide 29 million by this number in the denominator. So 29 million divided by 186,500. That gives me 155.5 approximately seconds. Be careful, it's seconds, okay? Because the natural unit for time is seconds. And now if I want to compute how many minutes that is, I can divide it by 60, and this gives me 2.59 minutes. Okay? This is the first car. Second car, we have a power of 180 horsepower, so it's 180 times 0.746. Okay, 180 times 0.746. This is now 134,280 watts. Okay? Are you following me?
Yes.
Yes. And so now the time taken
Yes, we're
by
following.
the second car is going to be the same energy, because I took cars which have same masses. Otherwise we would also need to look at the effect of the mass. 29 million joules divided by 134,280, and of course this is going to give us a longer time. Okay, 29 million divided by 134,280. This is approximately 216 seconds, which is about, if you divide by 60, it's about 3.6 minutes. And now you can compare these two results, and you see clearly that the car who has less power is taking more time to go up the mountain path. Okay, it can produce less energy per second, so it will take him more time to produce the energy which is necessary to go up. Okay?
Okay.
Okay. Good. Okay. This was for power. We will do more exercises with power later when we know more things. Now I want to go into a new section, which is potential energy. Okay, potential energy. Well, you have heard these words before, but you don't know exactly what potential energy is. Well, it is actually what it means. Okay, potential energy. Potential energy. It means that this energy is contained in a system. It's contained in a system which can release it in some form. Okay? When you say of somebody that he has a lot of potential, that what does it mean?
That he can do a lot of stuff.
Yeah, he can do a lot of things. Hello, Emmanuel. It's Emmanuel, right?
Hello.
Huh?
Yes, I've been here for a while.
Yeah, but I didn't hear you. I didn't recognize your voice yet.
Yeah.
Okay, so you can have potential energy stored in many systems. It's not just, it's not something that is specific to mechanics. You can have potential energy in various systems. Of course, in mechanics, let's take an example. Okay, if you have a rock, let's say a mass, and this mass is above the ground at some altitude h. this mass here is going to is containing potential energy, because if you let it fall, during the fall, this potential energy will transform into kinetic energy, and when it hits the ground, it's going to make a hole, it's going to produce some explosion, depending on which height you have. Okay, but the higher the mass, the more potential energy it has. Okay, the higher the mass, the more potential energy it has. Okay, that's one system which has potential energy. Can you guess another system which contains potential energy? Maybe. No? Okay, I'm going to give you another example. You take a spring. You take a spring, and there is nothing attached to the spring, so it has its natural length. Okay, and now you attach a mass to this string. What happens with the energy? Does this spring have some energy contained in it? Well, the answer is yes, it has, because if you remove the mass, the spring is going to go back to its initial length, and so it's going to produce a force in doing that. It's going to produce a force on a certain distance, so it's going to produce energy. Okay, so you can store energy in a spring. Let me give you an example, a domestic example. You take a rat trap. Did you see a rat trap, how it's done? Did you ever see a rat trap? Hello?
Yes, I have to, yes.
Okay, a rat trap is, it has a coil, it has a spring. Ah, yeah. A rat trap, it has a spring here. It has a spring, and it has a metallic frame, and this voilà. And this metallic frame is held by a little piece of metal here, and this piece of metal is attached to a piece of cheese. Okay, and so when the mouse comes, oh sorry, my mouse is horrible. When the mouse comes and she wants to eat the cheese, then she's going to move this. This hook is going to no longer hold the thing, and the thing will close and trap the mouse. Okay, so if you want this to close and to trap the mouse, you need energy. For any physical process, you need energy, and this energy is stored where? It is stored in the spring. Okay, so a spring can store energy, right? Yes? Are you convinced?
Yeah.
Okay, and so this spring contains a potential energy. Actually, the potential energy of a spring is given by 1/2 kx squared, where k is the rigidity constant of the spring, and x is the deviation, is the lengthening of the spring with respect to its initial position. So you see, it's an expression which is similar to what? You remember that formula? It looks like something else, which we wrote already. It looks like kinetic energy. It has a bit the same form, but of course this is completely different, because this is a potential energy, not a kinetic energy. Right? So example 1 was a mass, example 2 was a spring, example 3, I can give you an example which is linked with the course of electricity which we finished. Okay, if you take a capacitor, you remember a capacitor? Un condensateur, you remember how that is made?
No.
It's two metallic plates. Of course, the metallic plates, they have they have certain sizes, okay? They are like this. I'm just drawing them from the side. It's two metallic plates, and if you put a generator here, you will have the minus, the electrons here, and you will have electrons missing here. So actually all the wire and the plate on the side of the plus pole is going to be charged positively, and here we will have an excess of electrons, okay, and the electrons will accumulate here, and there is no current which can go from here to here, because in a capacitor there is no contact between the two plates. Here in the middle there is usually either air or a substance which makes the capacitor work better. I mean, gives it a better efficiency, right? So this system, if you charge it and then you remove the generator, so you will be with a capacitor which is not connected to anything. On one plate you have positive charges, on the other plate you have negative charges. And what happens if now suddenly you connect this capacitor which is charged to a lamp? What do you think happens? Silence. What happens? Tell me.
Energy.
Yeah. This capacitor is going to give us back the energy it contains, because here you have a lot of minus charges which have accumulated, and minus charges, they hate each other. They don't like to be close to each other. So these minus charges, they are going to do what? They are going to flow down here, and they are going to flow inside all the circuit, and they are going to come here, and they are going to compensate these positive charges, because positive charges are just atoms with missing electrons. Okay, it's not protons. Positive charges are electrons missing. So the electrons which are here are going to come to the other side, fill these holes, and the capacitor will discharge. But in discharging, he will produce a current, and that current is going to make the lamp bright. So the lamp is going to produce radiant energy and also heat. And so there was initially energy in the capacitor, and this energy, when we connect the capacitor to something, this energy is transferred to the circuit. Okay, so a capacitor can contain energy. A battery too. Okay, a battery contains a certain energy. Okay, when you have a battery, it's charged, and you have one pole here which is negative, one pole here which is positive, and so when you connect it to a lamp, there will be a current passing from plus to minus, which means electrons are going from minus to plus. The lamp will burn, it will produce energy, and so this means there is energy in the battery. Okay, and this is potential energy. This is potential chemical energy. This is potential electrical energy, electrostatic energy. This is potential spring energy, and this is potential gravitational energy. It's all different forms of potential energy. Okay? Okay. Oh,
Yes.
good. So that was the discussion. That was the discussion about potential energy. Okay?
Oh, that wasn't too long.
Yeah. Now you can read that if you want. I'm not going to read the course aloud for you. Okay? This is not very pedagogical. Now let's see how work is connected to potential energy. Okay? You remember that work is the scalar product of force times the distance. Okay, so work is a form of energy. Okay, and what we are going to do here is we are going to look at the work of the gravitational force when we lift a tomato and then when we let it go down. Let's look at that, and then with that we will be able to define the potential energy. So let's take, I'm now redoing this sketch here Okay, I'm redoing it. We have a tomato. We have a tomato, and this tomato has a certain mass. We lift it up, and then it goes down again. Okay? What are the forces that apply? Well, there is a gravitational force acting on the apple, and if we want to lift this apple, we need, of course, to apply a force in the opposite direction, and this force is just going to be minus the gravitational force. Okay? Right? Good. Now let's compute the work. Let's compute the work of the gravitational force, and let's compute the work of our force F. You remember, I told you very clearly, when you compute work, be clear about which force you are computing work for. Because if you compute the work of the gravitational force, it's going to be the opposite sign of the work for the force F. Okay? So let's compute the work of the gravitational force. It's the gravitational force scalar product with the distance. Okay? What's the angle between the gravitational force and the distance? Hello? Has everybody gone or what?
I don't know.
No.
No, we're just confused. Uh-oh.
Oh no, there are people. There are people, but I feel so lonely. Give me some feedback.
I'm just very confused.
Yeah, listen, I'm alone here all day long. At least when I teach, give me the impression that I'm with somebody, virtually. Okay.
Give me your dog again.
Huh?
Give me your dog again.
My dog. He's outside. He's outside. If you want, at the end of the class, I will go get him if you want.
Can we talk what would happen if we pass the year due to coronavirus?
What you mean if you pass the year?
What's going to happen for next year? Like, genre les bases, genre avoir les bases pour l'année prochaine.
Yeah,
Genre, on fait comment ça va se passer?
if you want to have the basis, just follow the class and work on it, and that's all. I don't know how it's going to work with the exams, because anyhow the decision does not depend on me. It's taken much higher than me. Okay, but the problem with this semester is that if the schools are very tough with examinations, the students who don't pass, they will do a recours. I don't know the word in English. They will do a recours, and it's going to be very difficult to refuse that recours, because indeed the conditions have not been good. Okay, if a student says, I couldn't work at home because my parents were fighting all the time and they were drunk and they were hitting me,
Oh, damn.
of course you have to accept that. No, but it happens. Okay, maybe it doesn't happen in your families, but in some families it happens. And so we cannot be very strict and then have everybody doing recours and accepting all the recours. It can be a mess. So I guess the DIP will be less strict, but I don't know how.
Je pense pas qu'ils vont faire redoubler autant de personnes, personnellement.
En tout cas, Niki, ouais.
Parce qu'en fait...
Non, mais Niki aussi.
Oui,
Mais Niki is a bit special.
Il y a peut-être une chance qu'il passe.
oui, non, mais en fait, mais en fait, genre, le Niki, de toute façon, il a déjà prévu de faire l'année. Mais le truc, c'est que ça leur coûte, en fait, genre, au niveau de l'argent, ça leur coûte assez cher un élève à l'année. Donc rien qu'en fait de le faire redoubler, ça va leur coûter cher.
Yeah.
Mais puis, je pense qu'ils vont plutôt se concentrer sur les quatrièmes qui ont leur examen de maths.
Yeah, the maturity exam, either they will do it in a very big room like Spalexpo with sufficient space between the people that they could do, or maybe we will do oral exams. via webcam. I don't know, but we don't know. We don't know nothing.
I think all is not possible.
Ouais, voilà.
Sorry.
Donc au pire, on le laisse passer comme ça, voilà, tu vois.
I think all is not possible.
We will see, but for the moment, do your work. Okay? Can I continue?
Can we hear that?
So let me go back to my thing here.
Le fat vent.
Okay. So the work of the gravitational force. The work of the gravitational. Hello. The work of the gravitational force is the gravitational force times d times the cos of 0. The cos of 0 is 1. The gravitational force is mg, and so the work of the gravitational force. Oh, sorry, I said something very stupid. The angle here is 180, so it's minus 1, and so, excuse me, the work of the gravitational force is minus mgd, where d is the distance.
Violent.
Okay? Okay. Now, what is the work of the force F, which is pointing up? This is the force we are giving with our hand to the tomato when we lift it. Okay? Well, the work is F scalar with D, but now F is going up, D is going up, so it's F times D times cosine 0, which is 1, and the force, we said it has the same magnitude as the gravitational force, so this is mgd. Okay, so finally what you find is that the work of the gravitational force is minus mgd, and the work of this force F, which opposes the gravitational force, is plus mgd. Right? Now we get to the definition of potential energy. Definition of potential energy. This is the mechanical potential energy, of course. We say, and this is what you can see on your course at the next page, we say that delta U, which means the final potential energy minus the initial energy, is minus the work of the gravitational force. This is the definition. Okay? U is the potential energy. You can call delta U the difference in potential energy when you lift your tomato. So this delta U is the final.
Why would we lift a tomato?
You can lift what you want. You can lift an apple.
Ouf, j'ai eu peur.
Personne, c'est toi.
C'est qui me rappelait.
C'est toi.
Oh, on peut voir votre chien.
Okay? So the delta U is minus the work of the gravitational force. The work of the gravitational force, we computed it here. There was a minus in front of it, and so this minus here is just to remove the minus that there is there, and so delta U, which is the final U minus the initial U, is just mgh. This is the final formula that you should remember. Okay?
Okay. Okay.
Now here we have final and initial. Okay, so let's compute now and simplify this a bit. Let's imagine your tomato. It was here, and you lifted it up to here. Okay, and this is y initial, this is y final, because here we have a vertical axis which is the y-axis. Okay, so the position. Who is speaking? I'm hearing a telephone conversation somewhere. No? Don't you hear it?
Non, enfin si, mais si, moi je crois.
Maybe it's one of you on the microphone or an echo,
On est
whatever.
tous, enfin, on est tous mute, donc je pense que ça vient de vous. Hein. Je pense que ça vient.
Yeah, I don't know. Okay, so let's imagine we are lifting this tomato which has mass m from a certain altitude to a higher altitude. Okay, so here we would define the final potential energy as mg times y final. We would define the initial potential energy as mg times y initial. Okay, and so the delta u is the u final minus the u initial, and now you can compute that. This is going to give you mg times y final minus y initial. Okay, and this quantity here we just call it h. Okay, so what we do is that we usually define somewhere as somewhere which is the initial altitude. Okay, and usually we define it to be 0. In terms of potential energy, you can put the 0 level wherever you want, and then the potential energy of something with respect to that 0 level is going to be just the mass times g times the altitude of that thing. I don't know if I explained this correctly. Let's imagine here you have the ground, okay, and here you have an apple tree, and on the tree you have an apple. Okay, so what you do in this kind of case is that at the level of the ground you say that the initial potential energy is 0. Okay, so the only thing which will count is the height here at which your apple is with respect to the ground, and so the potential energy of this apple will just be mgh. This is the formula you need to remember. The potential energy of an object, it's defined with respect to a 0 altitude, to an altitude where you define that potential energy is 0, and then you compute your potential energies with mgh for any object which is above that. Okay? And this is exactly what we did for the car. If you remember, for the car we took, there was the mountain path, but we just took the height, because traveling horizontally doesn't make a difference. I will get into more details on that in a minute. It's the next section. Okay, for the moment I just want to remember that expression. And here with our two cars, here we had a certain potential energy for the cars, which is mgh, and the energy the engine needs to produce is the energy necessary to overcome, to give to the car this potential energy. When you lift something, you have to give it energy so that its potential energy can increase. Okay? Answer. Hello? Ah, no, because you know, from time to time this thing is disconnecting, and I'm never sure if you are still connected or not. So you should do just a little bit of noise so that I know. I'm going to tell you now one thing which I'm telling you a bit in advance, but why did I insist so much on potential energy? It's because we are going to define in a moment mechanical energy, and mechanical energy is the sum of kinetic energy and potential energy, and this mechanical energy is always conserved, which means if you have a system without friction, the sum of the kinetic energy and the potential energy is always the same. Okay? Just a brief example to illustrate that. I will talk about it again in the next class, but just a little example. If you take a pendulum, Pendulum? You know what is a pendulum, right? Hello?
Yes, we know.
Yes.
Okay.
Yes.
You take a pendulum, and I mean, if you don't have a good intuition with pendulums, do one on your desk and look at it. When is the velocity maximal in the pendulum? When it oscillates? At which point is the velocity maximal? Can you tell me?
When it comes back.
Quand ça fait.
Yeah, it means where on my drawing?
Bah, sur un côté, je sais pas, sur un côté quoi.
À gauche, left, milieu.
Here, when your pendulum arrives here, it stops. I'm sorry. Okay, let me do a pendulum. I will use this stupid IP camera that I received today, and it doesn't work. I cannot connect it. If I do, wait, where am I? If I do a pendulum, where does it stop the pendulum?
In the middle.
No, it stops here and here. The pendulum
Yes.
So not completely.
it has the maximal velocity here, and here the velocity stops because it arrives, it stops, and then it comes back, and on the other side also
D'accord.
the velocity stops. Okay, and the maximum velocity is down here. So now, how can you observe the conservation of kinetic and potential energy? Well, take this level and say that this level corresponds to potential energy 0. You can define, as I told you, the 0 of potential energy wherever you want, and so choose something that is easy to solve your problem. Okay, so here the energy, the potential energy is 0, means that the mechanical energy is just kinetic energy. Okay, there is no potential energy in that point, because we said that when we are at that point the level is 0. What about this situation here? The mechanical energy here is given by what? Well, here the mechanical energy is K plus U, kinetic plus potential, but the kinetic energy is 0 because the velocity is 0. So in that point where it's higher, okay, the pendulum has only potential energy, and same here in this point it's going to go up to a height high, and here the mechanical energy is just U. So you see, when the pendulum oscillates, it constantly transfers energy from the kinetic energy to the potential energy. Well, I should say differently, from the potential energy to the kinetic energy, then back to the potential energy, then back to kinetic, back to potential. Okay? It's just to give you some intuition. We will talk about that again. Now, there's another thing I need to tell you. Do you have questions about this, first of all?
No.
Okay.
Very good.
This is something very important. You know, conservation principles are extremely fundamental in physics. And the principle of conservation of energy is a very important one. I did not state it yet, it will come in a moment, okay? But it's a very important result. Okay, now let's talk about conservative and non-conservative forces. Have you heard of that? This has nothing to do with politics, okay? Conservative forces have nothing to do with Donald Trump, fortunately. What is this? When you have a conservative force, and you go from point A to point B, okay, you follow some path, okay, and let's assume there is a force which acts in a constant manner over the object that you are displacing. Well, what happens when you have a conservative field is that the work for going from A to B, the work does not depend on the path chosen for going from point A to point B. Okay, so I could take a path which is straight, I could take a path which is doing that, I can take a path which is completely crazy and which does this. Okay, the work you need for going from A to B does not depend on the path. This is typically the case with the gravitational force. I will give you an example in a moment. And when you have non-conservative forces, then when you go from A to B and you follow different path, okay, the work for going to A to B depends on the path chosen. Now, do you have examples in mind for a situation like this? What kind of force could do that? What kind of force could require more work when the path is longer? Any ideas?
Can you repeat?
Sorry, I didn't hear.
Can you repeat the question?
Can you repeat the question?
Yeah,
The question is, can you imagine what kind of force could produce this phenomenon that the work for going from one point to another depends on the path, and in particular it will be larger if the path is longer? What kind of force could that be?
What is this feeling?
It's friction. It's friction. Okay? Let's take this mouse. Let's take this mouse and wait. Let's take this mouse and move it on this table. Let's say there is a point A which is marked by this pen here, and a point B which is marked by the other pen. Okay, if I go from here to here on a straight line, I need a certain work to do that, and this work is going to be given by what? How would you compute this work? If I tell you that the friction force is 1 Newton, what is going to be the work for going from here to here? You can compute that. Come on. Huh? The work is the force times the distance.
Do your courses online last this long usually?
LOL!
Just a question.
Usually they last the same time as a normal course. Okay, so okay, let me go faster. Oh, it's already 4:30. God. Okay, let me. Okay, you don't want to answer, so I will do it. Here you have a friction force and you have a distance of what? 20 centimeters. If the friction force is 1 Newton, 1 Newton times 0.2 meters, it's going to be 0.2 joule. But 0.2 joule with a sign, because the friction force is opposing the motion, so you have a minus sign. Okay? So minus 0.2 joule of work. Now if I take this mouse and instead of going straight, I do this. Okay? I take a crazy path as if I was drunk. Is the work going to be higher or lower?
Truck.
Huh? Is it going to be higher or lower? Why lower? The path is longer.
No, it's
If the
higher.
path
Yeah,
is longer,
yeah, exactly. That's
the
what
force is always the same. It's 1 Newton, the friction force, but it's 1 Newton times the distance, which is bigger. So if your path is longer, the energy you need is longer. Okay? So the friction.
c'est ce que j'ai dit.
You said that? I thought you said the contrary. Okay. So
Pas du tout.
friction forces are not conservative forces. If you have a friction force, the path determines the quantity of energy you need. And this is a bad thing because it makes us lose energy, and we don't like friction in general. We are unfair to friction because friction allows us to stand on our shoes. If there was no friction between our shoes and the ground, it would be impossible to walk. So friction is useful, but when we do physical experiments, it bothers us. Okay? Now let me give you an example of a field which is conservative. Okay? And of course it's very nice for us if we have a conservative force field. Let's imagine the gravitational field. Okay? And I am going to draw the gravitational field like this. You remember we drew, we never did electricity, but the gravitational field, it's associated to a force which is always acting downwards. Okay? And now if I have a mass here at point A, okay, and I want to go to point B, which is up here, I can go straight, of course. I can go down here and then up, which is what we did in the previous exercise. I can go up and then horizontally, or I can follow a crazy creative path, or I can do this. Well, my claim is that if you do this in the gravitational field, the work needed on all these paths is exactly the same. And how can you understand that? Well, here the work on the horizontal section is 0. This I already told you, because the gravitational force is perpendicular to displacement. So here there is no work. And here we will need a work to go up, which is mgh. Okay? Now, if I do this, the work here will be what? The work here will be the force times the distance, scalar product, which is the value of the force, the value of the distance, times the cosine of the angle, and here maybe the angle is 30 degrees. So actually, this gives you the vertical projection, okay, and this gives h. So you have the force which is mg times h, okay, and you use the same quantity of energy to go here. And then if you do that, every time you go up you will lose some energy, but every time you come down you will gain some energy. The mass that you are moving will give you back some energy when you come down. Okay, and then you go up again, then you come down again, you come up again, you come down again, and all this compensates, and so the work along that path is also going to be mgh. Okay, and this gives you the reason why for the cars, instead of following the route which goes to the path, I said okay, let's go straight down and then up, because whichever is the path, I can compute it like this. So this teaches us that if we need to compute the work from here to here, since all paths have the same work, take the path which is easiest for the computation, and this path is the path which is horizontal and then goes up vertical. Okay, are you there? Is anybody listening
Yes.
Ah, good.
We always are.
Good. Okay? Okay. So now I will you give me 5 more minutes. We will do one exercise and then I will give you one. Pardon? Just one. I will just flash it to you because anyhow you have the correction. This is an exercise which says the same that I've been saying just before, the same that I've been saying with the exercise of the 2 cars. Okay, you have a gravitational field and you have a mass which is going from point A to point B, and it's going to go along this path. But since it's in a conservative field, what we can do is to compute the work by using a path which makes computation simpler, and this path consists in going horizontally and then going down. When you are going horizontally, the work is 0. When you are going down, the work is mgh, where h is the distance, the vertical distance. So actually you can compute, but you have the correction here, you don't need to write it down. You can compute that the work of the gravitational force is Fg times d, and so you find 16 joules. And you don't need to know anything about this path to compute that. You can just use another path if the field is conservative. Okay, so look at that. And yeah, I have to finish now, otherwise you're going to scream and complain with your union. So I would like you, so we are at the same point as the other class, I would like you to do this exercise as homework for the wait, shall we meet next week or the holidays start on Thursday?
No, we don't meet.
We
Thursday
don't meet.
holiday.
It's going to be terrible. Thursday classes are always a mess. Okay, so this is not going to be for the 7th. This is going to be for the 22nd. Is that correct?
Can you put it on Classroom?
Yes.
Okay, I will put it. Also, I will put a message with the link to the video which I did today, which is a bit more slow. Maybe you will prefer it to the video I did for the Monday class, and I will also check the date for the homework and give you the homework. I will do that right now. Okay?
Okay.
Okay, so be good boys and girls. Don't do crazy things. Not now.
Mister, I have a question.
Yes. Tell
But
me.
it's about h9h10.
Yeah, tell me.
Will we have to do a lot of calculations about forces and power?
No, it's not about forces. There will be some calculations, but it's easy one. Okay, you can easily do the OC physics with if you are in Math 1. You don't need to be in Math 2 to do OC physics. But wait, you are in the 2nd year, so you already chose it. Or you are choosing it now. No, you are choosing it now. Okay. Yeah, how did it work? Because there should have been a presentation. They did it via Meet, or what did they do?
No, they didn't.
No, they just cancelled it.
Yes, and they gave some information we could ask
They gave
and
the petit, la petite
PDF.
brochure, là.
And you have to choose and send an email somewhere or something like that.
Yeah.
No, listen, the OC physics is not something complicated mathematically. Okay?
Okay.
So don't be afraid of math. If you want to take that, take it. It's interesting. Sorry?
Easier than what we do right now? Is it easier than what we're doing right now?
Right now in the course we are at a point where it's a bit conceptual. No, I wouldn't say it's easier than that. It's a bit the same. Okay? But you should
Okay.
you should choose based on your interests rather than based on what is easier and what is not easier. No, you don't think so? Listen, last year
Yes,
when
but that's what I need to take, but maybe it's too difficult for me to take it. That's the problem.
it's not difficult, and the grades. I mean, we don't kill the students with grades in the OC. When I gave the course, everybody passed except one girl who hadn't gotten anything. I mean, she was really completely à l'ouest, and so that one didn't pass. I mean, she didn't have a 4, but all the others they had 4 or more. Okay, it's not a drama.
Okay.
The grades. Don't worry. Okay, what do you want to study later?
I want to be a doctor.
So if you saw in the program this year, there is some medical physics, right? I think. Yeah. So
Theory.
yeah, you have the program. I think that
What did you say, sorry?
I think that Mrs. Chong is giving a course about medicine, preparation to medical exams. Look at the program exactly.
Yes,
Okay.
that's exactly why I wanted to take
Yeah.
physics.
I think it's a good idea. Well, you have to make a decision between chemistry, biology, and physics. Chemistry, biology, you are going to do it anyhow when you start university. Okay, so maybe if you have a better background in physics, it would help, because the first year physics exam is usually the one that kills most medical students, like 50%. Okay, this is the most feared exam in the first year. So, huh?
No, nothing.
So having a good background in physics is a good idea. Okay?
Okay. Yes, thank you.
You're welcome. Okay, so I will put the video online, and I will not see you probably before the Easter holidays. It is very possible that one of these days I will pop up with a very nice idea to do a grade based on work you can do at home. I will think about that. Okay, and I will keep you posted. No, we could do a lab at home or something. We will see. Yeah, easy. I received an email from our director saying that we should not exaggerate and not have too much work, because for some people the situation can be difficult. So no, we're not going. I'm not going to kill you. At least not me. Maybe my colleagues, but I don't know. Okay. Okay. Bye bye. Have a nice day. Bye
Have
bye.
a great vacation.
Bye bye. Thank you. You too.